Far out beyond Neptune, a frozen world named Orcus hides in the cosmic dark. This distant dwarf planet is one of our solar system's greatest puzzles, a place of gleaming ice and profound secrets. We are about to unravel 25 of its most mind-bending mysteries, from a moon that defies explanation to the possibility of hidden oceans beneath its crust. You will discover why this lonely world is so much more than a simple ball of ice. Why does its surface shine like a cosmic pearl while others lie in darkness? What is the true nature of its mysterious, oversized companion? Which cosmic mystery do you find the most compelling right now? That brilliant gleam from Orcus is our first great puzzle. This distant world does not simply reflect light. It throws it back with the intensity of a cosmic mirror. Scientists call this property albedo, which is just a measure of how much light a surface bounces away. Orcus possesses one of the highest albedos we have ever seen in the Kuiper Belt. Imagine a perfectly clean field of snow under a bright sun. That is the kind of reflective power we are talking about, but located in the perpetual deep freeze at the solar system's edge. This makes Orcus a shining pearl against an endless velvet blackness, a beacon of pure white that should not, by all rights, be so pristine. What could possibly keep its surface so clean and bright over billions of years? The leading theory points to fresh water ice, but that answer only leads to more profound questions. Water ice in the vacuum of space should be darkened by constant bombardment from cosmic radiation and micrometeorite dust, yet Orcus remains defiantly brilliant. This suggests something is actively renewing its surface. Perhaps internal geological forces are at work, pushing fresh ice from a hidden interior to the surface in a process known as cryovolcanism, where volcanoes spew water and ammonia instead of molten rock. Or maybe the ice is somehow constantly resurfacing itself through seasonal sublimation, where it turns directly from a solid into a gas and then refreezes, creating a bright new layer. Either scenario implies that Orcus is not the dead, frozen ball we once assumed. It might be a world with a complex and active history, its gleaming face hiding a heart that still beats, however slowly. The sheer brightness of this lonely world is our first clue that there is far more happening here than meets the eye. That brilliant, reflective surface might be hiding an even deeper secret, one that breathes. Scientists now suspect Orcus could possess an atmosphere, but not a permanent one. This would be a vanishing shroud of gas, appearing and disappearing in a cosmic rhythm tied to the dwarf planet's strange path around the sun. Its orbit is not a perfect circle, but a long, stretched ellipse. For a small part of its 248-year journey, Orcus swings slightly closer to the sun's distant warmth. During this brief period, the feeble solar energy might be just enough to heat patches of its surface ice, causing them to vaporize directly into gas. This process, called sublimation, could create a thin, temporary atmosphere. Then, as Orcus continues along its elongated path and retreats back into the profound cold of deep space, this delicate gaseous envelope would likely freeze solid once again, collapsing back onto the surface as fresh frost. This cycle of exhalation and silence would make Orcus a world that periodically comes to life, only to fall still once more. The scientific debate centers on what gases could possibly be involved. Water vapor is a prime candidate, but other volatile compounds like nitrogen, methane, or carbon monoxide could also be lifting from the surface. Detecting this fleeting atmosphere is one of astronomy's great challenges. It requires instruments to catch Orcus at the precise moment in its orbit when this ghostly shroud is present. Confirming its existence would transform our understanding of this distant object from a simple ball of ice into a dynamic, breathing world with active seasons, even if those seasons last for generations. The very idea that a world so far from the sun could have any atmosphere at all pushes the boundaries of what we thought was possible in the frozen outer darkness. The gleaming surface of Orcus is not its only companion in the dark. Circling this icy world is a moon so substantial it challenges our very definitions. Its name is Vanth, and its presence is deeply puzzling. Most moons in our solar system are minuscule compared to their parent planets. Our own moon is roughly a quarter of Earth's size, a ratio that is already considered unusually large. But Vanth is different. It is estimated to be nearly half the size of Orcus itself. This is not a small rock orbiting a giant planet. This is a pairing that looks more like two worlds dancing together. The size ratio is so close that some astronomers argue the system should be classified as a binary dwarf planet, a twin pair of frozen worlds locked in a mutual gravitational embrace. Visualize, if you will, our Earth with another world half its size whirling around it. The sky would be dominated by this colossal partner. That is the kind of dynamic we are witnessing here, far out in the Kuiper Belt. This extraordinary partnership immediately raises a profound question of origins. How did such a large moon come to be? One compelling theory is a giant impact. Perhaps in the violent early days of the solar system, a massive object slammed into a proto-Orcus, blasting a huge chunk of material into orbit that later coalesced into Vanth. This is how we believe our own moon formed. Yet, the sheer size of Vanth makes this a spectacularly violent event to contemplate. Another possibility is that Vanth was not born from Orcus at all, but was an independent object, a small world minding its own business in the Kuiper Belt, until it was gently captured by Orcus's gravity. But gravitational capture of such a large body is incredibly difficult, requiring a very precise and unlikely celestial dance to slow it down without it simply shooting past. The existence of Vanth forces us to reconsider what we know about the formation of these distant icy bodies. Is it the product of a cataclysm or a cosmic coincidence? The answer lies in the subtle details of their orbit and composition, clues that we are only just beginning to gather. The dance of Orcus and Vanth is not just a matter of size. It is also a tale of two colors. While many of its Kuiper Belt neighbors, like the famous Pluto, display a distinct reddish hue, Orcus presents itself in a far more neutral shade. Its surface is a pale, almost grayish-white, a stark contrast to the ruddy complexion of other distant worlds. This color conundrum is a direct window into the composition and history of this icy sphere. The reddish tint on places like Pluto is often caused by a class of molecules known as tholins. These are complex organic compounds that are not formed by life, but are created when simple ices like methane are bombarded for eons by solar radiation and cosmic rays. It is a sort of cosmic sunburn, a chemical change that paints the surface over billions of years. So why is Orcus so pale? One possibility is that its surface is simply different. Perhaps it is covered in a purer, cleaner form of water ice that does not contain as much of the methane required to create those reddish tholins. The constant renewal of its bright surface, which we discussed earlier, could be actively scrubbing away these colored compounds, preventing them from building up. Think of it like a fresh snowfall covering over old, discolored ground. Another theory suggests that Orcus is just as ancient as Pluto, but its specific orbital path, or even its own internal geology, keeps it looking pristine. The subtle color variations we can detect across its surface are the key to this puzzle. They might indicate patches where fresh ice has recently been exposed, right next to areas where the cosmic sunburn has begun its slow work. The neutral color of Orcus does not mean it is devoid of interesting chemistry. It just means its story is written in a different ink. It tells us that the processes of surface renewal here are powerful and persistent, effectively holding back the relentless darkening that paints the rest of the outer solar system in shades of red and brown. This pale visage is a shield, protecting the secrets that might lie just beneath. The pale surface of Orcus is a map of its present, but its path through the heavens tells a story of its ancient past. This distant world does not wander alone. It is locked in a precise gravitational dance with the solar system's ice giant, Neptune. Orcus is caught in what astronomers call a 2 to 3 orbital resonance. For every 2 complete orbits that Orcus makes around the Sun, Neptune makes exactly 3. This cosmic rhythm places Orcus in a very exclusive club, a dynamical group where Pluto is its most famous member. This relationship is the key to its incredible stability over billions of years. Think of it like 2 runners on a circular track, one much faster than the other. If they were not coordinated, the faster runner would eventually lap the slower one, causing unpredictable gravitational nudges. But in this resonant dance, every time Orcus completes 2 laps, Neptune completes 3, and they always meet at the same points in space. This repeating alignment prevents them from ever getting too close, ensuring their paths never cross in a dangerous way. This resonance is not a coincidence. It is a fossil record of the solar system's most chaotic era. The leading theory suggests that in its youth, our solar system was a far more dynamic and crowded place. The giant planets, Jupiter, Saturn, Uranus, and Neptune, are thought to have migrated from their original orbits. As Neptune moved outward, its immense gravity swept through the primordial Kuiper Belt, scattering countless icy bodies, but some, like Orcus and Pluto, were captured into these stable resonant orbits, like a clock being wound and set for eternity. The very existence of Orcus in this precise rhythm is a powerful clue, confirming that this great planetary migration truly happened. Its orbit is not just a path, it is a living memory of the solar system's violent birth, a rhythmic heartbeat echoing from a time of giants. That pale, uniform color we see from a distance may be a beautiful illusion. Look closer, and the surface of Orcus might tell a tale of 2 very different hemispheres. Subtle variations in its brilliant reflectivity hint that one side of this world could be markedly distinct from the other. Imagine a cosmic ball that is not identical all the way around, but has a face that is subtly brighter or darker than its back. What could create such a stark division on a remote dwarf planet? One leading theory points back to the idea of cryovolcanism, but with a twist. If geological activity is pushing fresh, bright ice to the surface, it may not be doing so evenly. Perhaps there is a single, massive cryovolcanic region, a frozen version of Yellowstone, constantly repaving one entire hemisphere with pristine white ice, while the other side remains an older, darker landscape. Another compelling possibility involves a slow-motion migration of ices across the surface. As Orcus travels along its elongated orbit, one pole might be tilted toward the distant sun for a long period, experiencing a relative summer. During this time, volatile ices like nitrogen or methane could sublimate from the warmer hemisphere, travel through that temporary atmosphere we discussed, and then refreeze onto the permanently shadowed, colder opposite hemisphere. This would leave one side stripped bare of its brightest frosts, while the other becomes a gleaming reservoir of freshly deposited ice. A third, more external force could also be at play. The Kuiper Belt is not empty. It is filled with microscopic dust and tiny particles. Orcus, as it moves through this debris, might have one hemisphere that consistently leads its orbit, acting as a shield that takes the brunt of this constant micrometeorite bombardment. This relentless sandblasting could darken the leading hemisphere, while the trailing side remains protected and bright. These are not just minor surface features, they are fundamental clues. A divided Orcus would be a world of dynamic processes, where internal heat, orbital cycles, and the environment of deep space all conspire to paint a globe with two different histories. The question of what its other side looks like remains one of its most compelling secrets. That pale, divided surface might be hiding its greatest secret, a profound absence of scars. When we look at other denizens of the Kuiper Belt, like Pluto's moon Charon, we see faces heavily pockmarked by billions of years of impacts. These craters are the hallmarks of an ancient, unchanging landscape, a cosmic history book written in violent collisions. Yet Orcus appears strikingly different, presenting a much smoother visage. This lack of large, obvious craters is a mystery in itself. Where are all the impact scars that should mark its ancient surface? This smoothness points to a world that is not static, but geologically active. Something must be actively erasing those craters, effectively giving Orcus a periodic facelift. One of the most fascinating possibilities is the glacial flow of water ice. We think of ice as hard and brittle, but over vast geological timescales, and under the pressure of its own weight, ice can behave like a slow-moving, viscous fluid. Imagine a block of tar left on a hot day, how it slowly sags and deforms over hours. Now picture that same process happening over millions of years on a planetary scale. The icy crust of Orcus could be gradually flowing, smoothing out the depressions left by asteroid impacts, filling them in until they vanish from view. Another compelling mechanism is that same cryovolcanic resurfacing we touched on earlier. If plumes of water and slushy ammonia ice are periodically erupting from its interior, they could flood vast regions, burying old craters under a fresh, gleaming layer, much like a volcanic flow on Earth covering an older landscape. There is also a process known as viscous relaxation. The icy shell of Orcus, warmed by faint internal heat or the pressure of overlying layers, might very slowly relax, causing any craters to sag and flatten out over eons. This would be like the slow, imperceptible smoothing of a dent in a memory foam mattress. The contrast with a world like Charon is stark. Charon's heavily cratered face tells us it has been geologically quiet for a very, very long time. Orcus, however, whispers a different story. Its smooth surface is a powerful clue that this distant world retains a source of internal energy, enough to reshape its own skin long after the era of heavy bombardment should have ended. This is not a dead world, but one that may still be slowly turning over, hiding its age beneath a deceptively youthful face. That remarkably smooth surface of Orcus is not just a visual puzzle, it is also a thermal one. This world exists in a realm of almost unimaginable cold, where temperatures should plummet to near absolute zero. Yet, the readings we have suggest it is slightly warmer than our most basic models predict. This temperature anomaly is a subtle but vital clue, hinting at hidden processes working deep within this frozen sphere. What could possibly be providing even a whisper of heat so far from the sun? One of the primary factors is the very brilliance we have already discussed. Its high albedo, a bright, reflective surface, naturally bounces away a great deal of the sun's feeble energy, which should make Orcus colder. But this is counteracted by other, more complex forces. The dark, empty void of space itself is profoundly cold, but the surface of a world can be warmed by sources other than direct sunlight. One of the most fundamental is the slow, steady decay of radioactive elements locked within its rocky core. Elements like potassium-40, thorium, and uranium release heat as they break down over billions of years. On a small world, this heat source is minuscule, but if Orcus is large enough and contains a sufficient amount of rock mixed with its ice, this radioactive warmth could be enough to nudge its internal temperature a few crucial degrees higher. This internal heat would then very slowly conduct outward, subtly influencing the temperature we can measure from afar. Even the sun, though it appears as little more than a bright star from that distance, contributes a tiny amount of energy. Furthermore, the composition of the surface itself plays a role. Different materials have different thermal properties. A layer of pure water ice will retain and distribute heat differently than a porous layer of nitrogen frost or a dark blanket of tholins. Measuring these thermal emissions is one of the greatest technical challenges in modern astronomy. Scientists must detect the faint whisper of infrared radiation, the heat signature, coming from an object that is smaller than our moon and over 4 billion miles away. This requires incredibly sensitive instruments on the world's most powerful telescopes, and even then, the data is often frustratingly ambiguous. The fact that we have any temperature reading at all is a triumph, and the fact that it does not perfectly match our simplest expectations tells us that Orcus is more than just a simple, passive ice ball. Its slight warmth is a signature of a world with an inner life, a faint but detectable pulse in the endless cosmic night. That subtle warmth we can measure is only one piece of the puzzle. To truly understand a world's composition, scientists turn to a technique called spectroscopy, which analyzes the unique fingerprints that different materials leave in reflected light. It is like listening to the whispers of the surface itself, yet when they point their instruments at Orcus, they are met with a profound silence. Its infrared spectrum is surprisingly featureless, lacking the strong, clear signals of specific ices that we see on other Kuiper Belt objects. This spectral riddle is one of Orcus's most baffling mysteries. Why does this bright, icy world refuse to reveal its ingredients? One compelling explanation is that its surface is masked. A thin, uniform layer of dark, radiation-processed tholins could be blanketing the cleaner ices beneath. Think of it like a fine, dark dust covering a field of pure snow. From a distance, the snow looks dark and muted, and its pure, reflective qualities are hidden. This layer would not need to be thick, just continuous enough to absorb the specific infrared wavelengths that would otherwise betray the presence of water or ammonia ice underneath. It creates a spectral smokescreen, obscuring the true nature of the world below. Another fascinating possibility involves the physical structure of the ice itself. On many cold worlds, water ice exists in a fine, powdery form that produces a very distinctive spectral signature. But if the ice on Orcus has been processed over billions of years by minimal heat and pressure, it might have sintered into much larger, coarser crystals. Large-grain water ice has a very different, much weaker spectral fingerprint. It is the difference between looking at a pile of fine white sugar, which appears very bright and white, and a single, clear block of ice, which can be surprisingly difficult to see specific features in. This theory of large-grain ice would also help explain the world's high reflectivity, as larger, cleaner crystals can scatter light more efficiently. So the spectral silence does not mean Orcus is empty or barren. It means its surface is either deliberately hiding its composition under a dark cloak, or it is made of a purer, more crystalline form of ice than we typically find. This riddle forces us to look closer, to find new ways to listen, because the secrets of Orcus are not given up easily. They are guarded by a veil of shadow or a wall of perfect, silent crystal. The origin of the Orcus and Vanth pairing is a cosmic whodunit written in gravity. To explain a moon so large, scientists turn to the most dramatic origin story available, a giant impact. Picture the early solar system as a chaotic shooting gallery, with countless protoplanets jostling for position. In one cataclysmic moment, a massive object, perhaps half the size of a young Orcus, slams into it at a glancing angle. The violence of this collision is almost beyond comprehension, a strike that would liquefy the outer layers of both bodies, blasting a colossal plume of vaporized rock and ice into space. Much of this debris would rain back down, but a significant fraction could be flung into orbit, where it would slowly coalesce under its own gravity, eventually forming the moon we now call Vanth. This is the leading theory for the formation of our own moon, and it seems a perfect fit for such an oversized companion. Yet, when astronomers run detailed computer simulations of this event for Orcus and Vanth, they hit a wall. The numbers do not quite add up. For the debris from such a violent impact to coalesce into a single, large moon like Vanth, the collision would have to be exquisitely precise. Too direct a hit, and both worlds are obliterated. Too glancing a blow, and the debris simply escapes into space. The resulting moon should also initially follow a very elliptical, elongated orbit. So how did Vanth settle into its current, remarkably circular path around Orcus? This circularity is a major puzzle for the impact model. Some process must have gently braked the moon, circularizing its orbit over billions of years. But what could provide that gentle touch in the emptiness of the Kuiper Belt? The other possibility, that Vanth was a free-floating object captured by Orcus's gravity, seems even more fantastical. Gravitational capture of such a large body is incredibly difficult. For one object to capture another, something must sap the excess energy from the system, like a third body acting as a gravitational brake, or complex interactions with a former ring of debris. The odds of such a perfect, gentle capture occurring naturally in the sparse Kuiper Belt are astronomically low. This leaves us with two profoundly challenging narratives. Was the system forged in a collision of unbelievable violence, followed by an eons-long period of orbital smoothing that we do not fully understand? Or was it born from an encounter of impossible grace, a cosmic dance where two independent worlds found each other against all probability? The truth of their partnership remains locked in their mutual orbit, a silent testament to a forgotten genesis. The silent partnership between Orcus and Vanth might be generating far more than just orbital stability. Deep beneath that frozen, reflective crust, the gravitational tug of war between these two worlds could be creating a hidden source of warmth. This leads us directly to the profound mystery of what lies beneath. Scientists construct models of distant worlds based on the scant data we have, and the most compelling picture of Orcus's interior is one of a layered world. It likely underwent differentiation, a process where the heaviest materials sank to the center, while lighter ones rose to the top. This suggests a dense, rocky core, possibly rich with radioactive elements like uranium and thorium. Encasing this core would be a thick mantle, not of rock, but of water in various forms. Closest to the core, the pressure and residual heat from radioactive decay might be sufficient to maintain a global subsurface ocean, a vast, dark sea trapped between the rock and the ice. Further out, this water transitions into a thick, rigid crust of water ice, the shell we see from the outside. But what could keep a liquid ocean from freezing solid over billions of years in such a frigid environment? The steady, gentle heat from radioactive decay in the core is one part of the answer. The other, more dynamic source could be tidal heating generated by Vanth. As the large moon orbits Orcus, its gravitational pull is not constant. It flexes the dwarf planet, stretching and squeezing its interior in a continuous, slow-motion massage. This internal friction generates heat, much like repeatedly bending a piece of metal warms it up. This tidal energy, combined with radioactive warmth, could be just enough to maintain a layer of liquid water, a subterranean abyss sealed away from the vacuum of space. Proving this theory, however, requires more than distant observations. The true test would come from a spacecraft flyby. By precisely tracking the probe's trajectory as it passes Orcus, scientists could measure tiny wobbles in the dwarf planet's gravitational field. These subtle tugs would reveal the distribution of mass inside the world, like a cosmic X-ray, a gravitational map showing a dense central core surrounded by a less dense mantle and crust, would confirm the differentiated model. Furthermore, by analyzing the exact shape of Orcus, whether it is a perfect sphere or slightly squashed, we could understand the rigidity of its icy shell and infer the presence of a softer, potentially liquid layer beneath. The possibility that this lonely, pale world could harbor a hidden ocean is staggering. It transforms Orcus from a simple relic of ice into a potential habitat, a dark, watery vault where the secrets of life's ingredients might be preserved in the eternal deep. Determining the true age of Orcus is like trying to read a clock that has been repeatedly wiped clean. Without physical samples to analyze, scientists turn to the traditional method of crater counting, reading the scars left by cosmic impacts to gauge a world's antiquity. A surface densely pocked with craters speaks of immense age, a landscape that has remained untouched since the solar system's violent youth. Yet Orcus presents us with that confounding smoothness, a visage with far fewer craters than expected. This forces a difficult question. Is Orcus genuinely a younger world, or are we simply looking at an ancient surface that has been constantly renewed, effectively erasing its own history? The answer ties this distant object directly to the most dramatic events in our solar system's past. Orcus likely formed over 4.5 billion years ago from the same swirling disk of gas and dust that gave birth to the Sun and all the planets. It is a primordial relic, a leftover building block from that initial construction phase. This means its true age is nearly as old as the solar system itself. However, its current surface might be a much more recent mask. That period of intense cratering, known as the Late Heavy Bombardment, was a time when the outer solar system was a shooting gallery, and every world bears its marks. If Orcus was geologically active for a long time after this era, through cryovolcanism or glacial flow, it could have resurfaced itself, burying those ancient craters under miles of fresh ice. In this scenario, Orcus is like an ancient castle whose original stone walls have been covered by modern plaster. The structure is old, but its skin looks new. Another, more radical possibility is that the original Orcus was shattered in a colossal collision, and the body we see today is a gravitational reassembly of the largest pieces, a phoenix risen from its own rubble. If true, this would mean the current Orcus is actually a second-generation object, with a formation date billions of years after the solar system's birth. So which is it? Is this pale world a pristine primordial fossil, its youthful appearance a brilliant deception, or is it a reconstructed survivor, a testament to cosmic violence and rebirth? The silence of its smooth surface holds the answer, a secret it has kept for eons. Amid the brilliant, uniform white of Orcus, a single dark blemish would change everything. Some interpretations of the limited data hint at a large, anomalous dark spot, a stark shadow on its otherwise gleaming face. This is not a confirmed feature, but a tantalizing possibility born from the faint whispers of light we can gather from Earth. If it is real, what could this shadow be? One possibility is a colossal impact basin, a scar from an ancient collision so violent it blasted through the bright surface ice, exposing a darker, deeper layer of material beneath. This exposed layer could be the rocky core of Orcus itself, or a concentration of those complex, radiation-darkened organic compounds known as tholins. Another explanation points to cryovolcanism, but of a different kind. Instead of spewing bright water ice, a past eruption might have released a slurry of darker, mud-like material rich in ammonia or carbon-based compounds, leaving behind a vast, frozen flow that stains the landscape. Or perhaps it is a region where the surface ice has been stripped away entirely, not by an impact, but by that slow migration of volatile ices we considered earlier, leaving behind a permanent, dark plain of bare, ancient material. The existence of such a spot would be a direct window into the inner workings of this world. It would tell us that the processes reshaping its surface are not uniform, that there are places where the bright, renewing ice has failed, allowing the dwarf planet its hidden history to show through. This mystery, more than any other, underscores the profound limits of our current vision. We are squinting at a tiny, pale dot 4 billion miles away, trying to decipher its secrets from the faintest flicker of light. The dark spot anomaly is a ghost in the data, a question that can only be answered by sending a dedicated mission to stare directly into the face of this distant, frozen world. That same brilliant whiteness might not be the only thing obscuring our view. Orcus could be hiding an even more ethereal secret, a ring system. We have already discovered that some small, icy worlds in the outer solar system, like the centaur Chariklo, possess faint, narrow rings. This revelation shattered the old idea that only giant planets like Saturn could host such features. The mechanisms for ring formation around a small body are surprisingly straightforward. A past collision with a smaller object could have kicked up a cloud of debris, or the gravitational pull of Orcus might be slowly tearing apart a tiny, unseen moon, feeding a steady stream of dust and ice particles into orbit. The real mystery is how such a ring could persist. In the crowded gravitational environment near a giant planet, shepherd moons often corral ring particles, keeping them in a neat band. But out in the lonely Kuiper Belt, the dynamics are different. The ring would be incredibly tenuous, a ghostly halo of fine dust and ice crystals. Detecting this from Earth is one of astronomy's greatest challenges. The rings would be far too faint and close to Orcus to be seen directly by any telescope we currently possess. So how could we ever find them? The answer lies in a celestial event known as a stellar occultation. This occurs when Orcus passes directly in front of a distant star. For a few precious seconds, the star's light winks out as the dwarf planet blocks it. But if Orcus has rings, something extraordinary happens. Just before and just after the main event, the star's light would flicker. Those faint rings, invisible to our telescopes, would briefly dim the starlight as they passed in front of it. It is like holding a delicate, crystalline necklace up to a single, brilliant light bulb in a dark room. You might not see the necklace itself, but you would see its intricate shadow. Catching such an event requires an immense amount of luck and precise coordination, as the path of the shadow Orcus casts on Earth is narrow. Astronomers must deploy teams of observers across the globe, hoping one will be in the perfect spot to witness the telltale flicker. A confirmed ring around Orcus would transform our understanding of this distant system, revealing it to be a place of ongoing, delicate dynamism, where unseen forces are continually sculpting dust and ice into a silent, orbiting crown. The ghost of a cosmic cataclysm might still linger in the darkness, not on Orcus itself, but in the space around it. We now confront the possibility that this dwarf planet is not an orphan, but the largest surviving member of a vast, shattered family. After the hypothetical collision that may have created Vanth, the debris field would have been immense. While the largest pieces coalesced into the binary we see today, countless smaller fragments would have been flung outward, all sharing a nearly identical composition and a common origin. This is known as a collisional family, a celestial dynasty born from a single, violent event. Finding these long-lost siblings would be the ultimate proof of that ancient impact. Yet, in the Kuiper Belt, this search is a monumental challenge. The outer solar system is divided into two populations: the cold classical belt with objects on stable, circular orbits, and the hot population where Orcus resides. The hot population is called that because its members have wildly inclined and eccentric orbits, all stirred up and scattered by the gravitational migrations of the giant planets in the distant past. This means that over billions of years, the gravitational influence of Neptune has acted like a cosmic blender, thoroughly mixing up all the objects in this region. Any family of fragments from a single collision would have been scattered across millions of miles, their orbital paths stretched and twisted until their familial resemblance was all but erased. Identifying them is like trying to reassemble a specific puzzle after its pieces were thrown into a hurricane and blown across a continent. You would need to track down objects that not only share a similar spectral signature, a similar color and composition, but also a similar orbital history that can be traced back to a single point of origin. So far, no definitive collisional family has been conclusively linked to Orcus. The silence is deafening, but if we could find one, it would be a revelation. It would confirm the violent impact theory for Vanth's origin beyond any doubt. More than that, it would give us a direct sample of Orcus's interior. By studying the composition of these smaller family members, we could know exactly what lies beneath that bright, icy crust without ever having to dig. We would be analyzing the scattered pieces of a world, giving us an unprecedented geological report on its hidden layers. The search for this lost family continues, a silent hunt for echoes of a shattering blow that reshaped a world and scattered its essence across the frozen frontier. Methane is the ghost in the machine of the outer solar system, and its elusive signature around Orcus presents a critical puzzle. On neighboring dwarf planets like Pluto and Eris, methane is abundant, painting their surfaces and contributing to their complex seasonal cycles. Yet for Orcus, the evidence is frustratingly ambiguous. The spectral data we have is too faint to confirm its presence definitively, leaving us to wonder if this world is fundamentally different from its cousins. The presence or absence of methane is far more than a simple chemical inventory. It is a direct probe into the world's deepest history and its current state of activity. Methane is a volatile compound, meaning it easily vaporizes into a gas. For it to exist as surface ice on Orcus, the local temperature must be consistently and profoundly cold, well below -230 degrees Celsius. At the slightly warmer temperatures we suspect for Orcus, methane ice should be sublimating away into space over geological time. So if we were to find widespread methane on its surface today, it would imply one of two incredible things. Either Orcus has managed to preserve a primordial supply of methane from the very formation of the solar system, a feat that would require it to have been eternally cold and geologically quiet, which contradicts its smooth, youthful surface. Or more likely, it has an internal source that is actively replenishing the methane we see. This could point to ongoing cryovolcanic activity, where reservoirs of methane deep within the mantle are periodically brought to the surface. The absence of methane would be equally telling. It would suggest that Orcus formed in a different region of the primordial solar nebula than Pluto and Eris, a region poorer in carbon-bearing ices. Or it could mean that any original methane has long since been stripped away by eons of sublimation or processed by radiation into those complex, dark tholins that mask its surface. This single question about a simple molecule forces us to choose between two dramatic narratives. Is Orcus a world still breathing out ancient gases from its interior? Or is it a relic from a different cosmic neighborhood altogether, its chemical story written in silence and absence? The answer lies frozen in place, waiting for a sharper gaze to read it. The rhythm of its light holds another secret. As Orcus spins in the darkness, its brightness does not remain constant. It pulses with a subtle but definite beat. Astronomers track this pulse by measuring its light curve, the precise graph of its brilliance over time. That regular rise and fall is a coded message about the world's true form. A perfectly spherical object with a uniform surface would show a flat, unchanging light curve, but Orcus is not that simple. Its light fluctuates, telling us the world we see is either not round, not uniform, or both. One possibility is that Orcus itself is significantly elongated, shaped more like a cosmic potato than a perfect sphere. If this is the case, as it rotates, we see more of its surface area when its long side faces us, making it appear brighter, and less when we are looking at its ends, making it dimmer. It would be like watching a tumbling log, seeing its full length one moment and just its tip the next. Another, equally compelling explanation lies in those surface albedo patches we considered earlier. Perhaps one hemisphere is significantly brighter than the other, covered in that pristine, reflective ice, while its counterpart is darker and duller. Every time the bright side swings into view from Earth, the light curve peaks, and it dips again as the dark side rotates toward us. This would be like watching a slowly spinning ball, half painted brilliant white and half painted charcoal gray. There is a third, more dynamic force at play, the gravitational hand of Vanth. The pull from such a large, close moon could be distorting Orcus's shape, creating a permanent tidal bulge. This would make the world slightly egg-shaped, and that asymmetry would also create a distinct signature in its light curve as the different faces turn toward us. The true mystery deepens when we look at the long-term data. The rotation is not a simple, predictable clockwork. There are complexities in the pattern, subtle irregularities that suggest the spin is more of a wobble, a slow precession, or a libration, like a top winding down. This could be the lingering echo of that ancient giant impact, a wound in its rotation that has never fully healed, or it could be the ongoing, gentle tug from Vanth, constantly tweaking its partner's spin in an eternal gravitational dance. The varying light of Orcus is a direct reflection of its turbulent history and its active present, a beacon whose flickers we are only just beginning to decode. The subtle wobble in its rotation is a fleeting tremor compared to the grand celestial dance that governs its path. Orcus's current resonance with Neptune is a stable arrangement, but the outer solar system is a dynamic and unpredictable place. Gravitational simulations that project millions of years into the future reveal that this stability is not necessarily eternal. The gentle, repeating tugs from Neptune, which currently protect Orcus, could one day become a source of chaos. The gravity of the other giant planets, especially Jupiter and Saturn, exerts a constant, subtle influence on this delicate balance. Over immense timescales, these cumulative nudges could slowly perturb Orcus's orbit, altering its trajectory in profound ways. The 2 to 3 resonance might be broken, setting the dwarf planet on a new and unpredictable course. This raises a startling possibility. Could Orcus one day be ripped from its frozen kingdom and sent tumbling inward? It might eventually join the population known as centaurs, those enigmatic icy bodies that orbit between Jupiter and Neptune. A centaur Orcus would undergo a dramatic transformation. As it drifted closer to the sun, solar heating would activate, turning its surface ice into a magnificent, temporary coma and tail, effectively becoming a giant comet. Its hidden oceans, if they exist, would begin to boil, and its entire geology would be thrown into turmoil. Yet, this journey inward is far from a guaranteed destiny. For every simulation that shows Orcus escaping, another suggests its resonance is a remarkably sturdy prison, a gravitational groove so deep it could persist for the entire remaining lifetime of the solar system. Its path may be one of eternal wandering within a vast but defined territory, a permanent sentinel of the frozen frontier. The true mystery is whether its dance with Neptune is a lifelong partnership or merely a single, long movement in a much grander symphony of motion. The ultimate fate of this cosmic wanderer remains written in the invisible equations of gravity, a future we can only model but never truly witness. One of the most thrilling possibilities is that Orcus could be an active world of ice volcanoes. Picture a volcano, but instead of spewing fiery lava and ash, It erupts with a slow, cold slurry of water ice, ammonia, and methanol. On the intensely frigid surface of Orcus, this slushy mixture would behave almost like lava, oozing across the landscape and freezing into strange, new geological formations. We might see vast, gently sloping domes built up over eons by repeated eruptions, or long, frozen flows that snake across the plains, their flow fronts standing like icy cliffs against the stark terrain. These would not be dramatic, explosive events, but a slow, geological weeping, a planet literally turning itself inside out. But what could possibly provide the heat to power such activity so far from the sun? The answer lies deep within. The steady, relentless decay of radioactive elements in its rocky core provides a foundational warmth, a faint but persistent geothermal heartbeat. This is then amplified by the gravitational kneading from its large moon, Vanth. As Vanth tugs on Orcus, it stretches and flexes the dwarf planet's interior. This tidal friction generates heat, much like repeatedly bending a piece of metal warms it up. Together, these two energy sources could be just enough to maintain pockets of slushy, liquid cryomagma trapped beneath the thick, icy crust. When the pressure builds too high, this cold magma could force its way to the surface, creating the very cryovolcanoes we imagine. For a future space probe, the hunt would be for specific, telltale landforms. It would scan for those distinctive domes with their central pits, or search for smooth plains that clearly overlay and bury older, cratered terrain. Finding such features would be a monumental discovery. It would confirm that Orcus is not a static relic, but a geologically living world, one that continues to reshape its own face in the profound and silent cold. The immense size of Vanth forces a profound question about the very nature of this partnership. Is it a moon orbiting a planet, or are we looking at something far more extraordinary, a true binary dwarf planet system? The distinction is not merely semantic. It is written in the invisible geometry of their dance. The key lies in a point called the barycenter, the shared center of gravity around which both bodies actually revolve. In a system like Earth and its moon, the barycenter lies deep within Earth's interior. Because our planet is so much more massive, the moon orbits us, and we merely wobble slightly. But when two worlds are close in size, the barycenter moves. For Pluto and Charon, the barycenter lies in the empty space between them, a clear sign of a binary relationship. For Orcus and Vanth, with Vanth being nearly half its partner's size, the barycenter almost certainly resides outside the main body of Orcus itself. This transforms their motion from a simple orbit into a mutual, graceful waltz through the void, two frozen spheres pirouetting around a common point in space. This dynamic directly challenges our traditional, Earth-centric definitions of what constitutes a planet and a moon. If a moon is so large that the system's balance point floats free in space, does the term moon even apply anymore? The argument for classifying them as a binary system is powerful, placing Orcus and Vanth in an exclusive club with Pluto and Charon. Yet, the debate is far from settled. Some scientists point to the remaining size difference, arguing that Orcus is still definitively the primary, the dominant gravitational anchor. Others question whether our current fuzzy data on their exact masses and diameters is precise enough to make a final call. This classification puzzle forces us to confront the beautiful complexity of our solar system, where neat categories often fail. Is this a planet with an astonishingly large moon, or are they twin worlds, forever bound in a silent, balanced embrace? The answer will redefine not just these distant objects, but our entire understanding of cosmic relationships. That brilliant, mirror-like gleam of Orcus is a deception that runs deep. We return to its surface to confront the albedo anomaly, the puzzle of why this particular world shines with such intensity, while so many of its neighbors languish in darkness. The contrast with an object like Arakoth is absolute. Where Orcus is a beacon of white, Arakoth is a deep, reddish charcoal, a primordial snowman that has been baking in cosmic radiation for billions of years. This difference is the key to understanding that Orcus is not simply a relic. It is a world that is actively fighting against the dark. The leading explanation remains the constant renewal of its surface by fresh, clean water ice. But how does this process work with such efficiency in a place of near absolute zero? One mechanism could be the slow, global process of glacial flow. The entire icy crust might be in a state of imperceptible motion, like a river of tar flowing over centuries, constantly bringing unblemished ice from the interior up to the surface, covering any areas that have been darkened by radiation or dust. Another, more dramatic possibility is the localized action of cryovolcanoes. These would not be towering mountains of fire, but broad, gentle domes that weep a cold slurry of water, ammonia, and methanol. Each eruption would pave over a vast area with a new, brilliantly reflective layer, a fresh coat of white paint on a cosmic scale. Then there is the theory of atmospheric condensation. We already pondered the possibility of a temporary, vanishing atmosphere. If this is real, then the cycle of freezing and thawing could act as a global resurfacing machine. As Orcus swings away from the sun, its entire thin atmosphere might freeze out, falling as a fine, bright snow that blankets the entire world in a uniform layer of pristine frost. This would be a seasonal refresh, a deep freeze that leaves the surface gleaming for its long journey back into the dark. But there is a third, more subtle hypothesis. It is not about new ice, but the specific nature of the ice that is already there. The water ice on Orcus might exist in an unusually large-grained, crystalline form. Think of the difference between fine, powdery snow and a single, clear block of ice. The powdery snow appears bright because of how its countless tiny facets scatter light in all directions. A clear block of ice is more transparent, but if the ice on Orcus has sintered into large, coherent crystals with incredibly smooth surfaces, it could act like a collection of tiny mirrors, reflecting light directly back with stunning efficiency instead of scattering it. This would make it appear brilliantly white to our telescopes, a world sheathed in a perfect, crystalline armor. The albedo of Orcus is not a single answer, but a battle between creation and decay. Its brilliance is a testament to the powerful, hidden forces that refuse to let this distant world fade into the obscurity of the dark. Deep within the data from the Hubble Space Telescope lies a ghost, an ultraviolet signal from Orcus that refuses to be identified. This is not a simple reflection of light, but a specific, energetic fingerprint in a part of the spectrum our eyes cannot see, a clue that the surface of this world is undergoing a strange and active chemistry. The sun's ultraviolet radiation, though incredibly faint at that distance, is still powerful enough to break apart molecules on the icy surface in a process called photolysis. When this happens to simple water ice, it can create a cascade of new and unexpected compounds. One of the prime suspects is hydrogen peroxide, the same chemical we use as a disinfectant on Earth. If ultraviolet light is splitting water molecules and they are recombining into peroxide, it would leave just this kind of spectral signature. This would mean the surface of Orcus is not a passive slab of ice, but a vast, frozen laboratory where light itself is cooking up bizarre chemicals. Another possibility points to the presence of more exotic surface ices, like solid nitrogen or carbon monoxide. These ices behave very differently under ultraviolet light than water ice does, and their unique electronic transitions could be producing the mysterious signal we detect. Finding nitrogen here would be a major discovery, linking Orcus more closely to worlds like Pluto and Triton, which are known to have vast plains of nitrogen frost. Yet the signal is faint and ambiguous, a whisper at the very edge of what Hubble can perceive. It is a perfect puzzle, a lock for which we do not yet have the key. This ultraviolet mystery is a direct challenge to our next generation of observatories, like the James Webb Space Telescope. Its powerful infrared eye will be able to stare directly at Orcus and break its light down into a far more detailed spectrum, potentially identifying the exact molecule responsible for this cosmic clue. Until then, the ultraviolet ghost remains, a tantalizing hint that the pale face of Orcus is hiding a chemical reality far more complex than we ever dreamed. The ultraviolet ghost haunting its surface is just one symptom of a world in constant, slow-motion flux. Orcus does not simply orbit, it breathes in a rhythm that lasts for centuries. Its highly elliptical path and probable axial tilt mean this distant world almost certainly experiences seasons, but these are seasons of an entirely different order. A single summer or winter on Orcus spans not months, but decades. As it journeys along its stretched path, the subtle changes in solar heat become the engine for a global transformation. For a brief period of its 245-year orbit, Orcus swings slightly closer to the Sun. The sunlight it receives, though still incredibly weak, intensifies by a small but crucial percentage. This is the trigger. On its surface, patches of the most volatile ices, like nitrogen, methane, or carbon monoxide, begin to warm just enough to sublimate. They do not melt into liquid, but turn directly from solid ice into a thin, tenuous gas. This process creates a temporary, ultra-thin atmosphere, a ghostly shroud that clings to the world for a generation. Then, as its long orbital journey carries it back into the deep freeze, this delicate gaseous envelope collapses. The atmosphere freezes solid once more, falling back to the surface as a fine, bright frost. This is not a gentle snowfall as we know it, but a global condensation event, a silent, slow-motion exhalation that leaves the landscape gleaming. This cycle could also drive a slow migration of ices across the globe. Imagine one hemisphere tilted toward the distant sun during this long summer. Volatile ices there would vaporize, travel through the thin air, and then redeposit as frost on the permanently shadowed, frigid poles, or the opposite winter hemisphere. Over decades, entire landscapes could be stripped bare, while others become buried under deep, bright reservoirs of freshly deposited ice. The surface we see today might only be a snapshot in this epic cycle, a single frame from a movie that takes 2.5 centuries to complete. What looks like a permanent feature from our distant vantage point could be a temporary state, a season that will last for a human lifetime before slowly shifting into another. This means the very composition and reflectivity of Orcus could be in a state of perpetual glacial change, its face slowly transforming with the passing of each cosmic year. The gravitational influence of Orcus may have sculpted the cosmic neighborhood around it. As one of the larger bodies in its region, this dwarf planet would have wielded significant gravitational pull during the solar system's formative years. Think of a massive ship moving through a crowded harbor, its wake gently pushing smaller boats into new positions. Orcus could have acted in a similar way, its gravity nudging countless smaller icy fragments, clearing out specific zones or herding them into more defined orbital paths. This concept casts Orcus not as a passive resident, but as an active architect, a gravitational sculptor that helped shape the very structure we observe in the Kuiper Belt today. Astronomers theorize that groups of objects like the Plutonos, which share Orcus's resonant dance with Neptune, might have been shepherded into their current orbits by the collective gravity of their largest members. Orcus, as a prominent Plutono, could have been one of these celestial shepherds. Its persistent gravitational tugs over billions of years would have acted like a cosmic comb, helping to maintain the sharp inner edge of the Kuiper Belt, or even carve out the relative gaps between different populations of objects. The scattered disk, for instance, with its wildly inclined orbits, might have been partially shaped by repeated encounters with giants like Orcus in the ancient past. This transforms our view of the Kuiper Belt from a simple collection of ice and rock into a dynamic system, a place where the largest bodies impose a subtle order on the chaos. The current arrangement of the frozen frontier could be the lingering echo of Orcus's ancient gravitational voice, a permanent signature of its role as a hidden architect in the dark. Our final mystery is the most frustrating of all, the simple fact of our own ignorance. We have gathered every possible clue from billions of miles away, but the true nature of Orcus remains locked behind a veil of distance. The ultimate solution is a mission we have not yet sent, a dedicated spacecraft on a multi-decade journey to this frozen frontier. Imagine a sophisticated probe, a robotic ambassador equipped with cameras sharper than the Hubble Space Telescope and spectrometers capable of sniffing out the faintest chemical whispers from the surface. Its primary goal would be a high-speed flyby, screaming past Orcus and Vanth to capture the first clear images of their alien landscapes. We would finally see if that dark spot is real, if cryovolcanoes dot the plains, and if Vanth's surface tells a story of capture or cataclysm. The spacecraft would map the entire system in exquisite detail, charting the subtle color variations and measuring the precise gravitational tug of both bodies to unveil their internal structure, finally confirming or denying the existence of a hidden ocean. But such a mission is a monumental undertaking. The journey alone would take 30 years or more, requiring immense patience and long-term commitment from the scientists who would begin the project and likely not live to see its triumphant conclusion. The spacecraft would need a reliable power source, like a next-generation radioisotope thermoelectric generator, to survive so far from the sun's warmth. And the cost would be staggering, a multi-billion-dollar investment in pure discovery. Every piece of data we have wrestled with, from its spectral silence to its orbital dance, is a mere postcard from a world we have never truly visited. The greatest mystery of Orcus is not on its surface, but here on Earth, in our collective decision of whether this distant, pale sentinel is worth the long, dark, and expensive voyage to finally meet it face to face. From its brilliant, mirror-like surface to the profound silence of its infrared spectrum, the 25 mysteries of Orcus paint a portrait of a world that defies simple explanation. This is not a dead ball of ice, but a complex and dynamic sphere that challenges our most basic assumptions about the outer solar system. We have journeyed through the puzzle of its oversized companion Vanth, a moon so large it blurs the line between satellite and sibling. We have contemplated the possibility of a hidden subsurface ocean, kept liquid by the faint warmth of radioactive decay and the persistent gravitational tug of that same moon. We have considered the evidence for cryovolcanoes that weep frozen slush, for a vanishing atmosphere that breathes in a rhythm of centuries, and for a surface constantly renewed by forces we do not yet fully comprehend. Its strange orbit is a fossil from the solar system's violent birth, its pale color a shield against the darkening of deep space, and its very warmth a signature of an inner life. Each of these 25 enigmas, from the ghost of a possible ring to the ultraviolet whisper of unknown chemistry, intertwines to reveal a world of astonishing activity and profound secrets. Orcus stands as a testament to the fact that the most fascinating discoveries are often hiding in plain sight, or in this case, in the distant, frozen dark. So we turn this final mystery over to you. With all these incredible possibilities laid bare, which one captures your imagination the most? Is it the potential for a hidden ocean, the dramatic story of its moon's formation, or the simple, brilliant mystery of its shining face. Share your thoughts in the comments below, and never stop looking up and wondering about the hidden wonders waiting at the edge of our own cosmic backyard.